Scientific papers can be difficult to read, especially when they use terms like standard deviation. In this video, we'll take a simple but deep look at this concept. Let's use an example to help illustrate the concept of standard deviation. Imagine we need to check the accuracy of a milk bottle filler. We could randomly select 8 bottles from the production line and measure the amount of milk in each bottle to analyze the consistency of the filling process. Assume that the first bottle contains 410 milliliters, the second one 390, and so on. When we calculate the average amount of milk in the bottles, we find that it meets the machine specifications at 400 ml. Some bottles, however, contain slightly more or less than 400 ml. To compute these differences, we can subtract the actual amount of milk in each bottle from the mean of 400. When we calculate the absolute value of the error, we see that the machine has an average error of 12 ml. But is the error from 8 bottles a reliable representation of the machine error across thousands of bottles per day? To try to answer this question, we use the standard deviation. The standard deviation is a combination of the mean error plus a safety margin. In our example, with 8 bottles, the mean error is 12, but the standard deviation is 14.4. So the mean error is 12 and the safety margin is 2.4 ml. Now, this safety margin is calculated using the concept of the degrees of freedom. In our initial calculations, we obtained the mean error by dividing the total absolute error by 6 bottles. Under the concept of the degrees of freedom, we divide the total absolute error by just 5 bottles. So instead of dividing the error by the number of observations, we divide it by the degrees of freedom, which is the number of observations minus 1, or in this case 5 bottles. In this table, we can see that the fewer observations we have, the greater the safety margin created by the degrees of freedom. As a result, dividing the error of 3 bottles by 2 yields a 50% margin, whereas dividing the error of 100 bottles by 99 yields a 1% safety margin. So the standard deviation changes based on sample size. If the observed error is 12, with more observations we'll be more confident that an error of 12 really reflects how well the machine works, and as a result our safety margin goes down. An important assumption for the use of the standard deviation is that the machine fills the bottles following a normal distribution, with 68% of the bottle containing plus or minus 12 ml. Also, 95% of the bottle contain between plus or minus 24 ml, and 99% of the bottle contain between plus or minus 36 ml. Because the standard deviation varies depending on the sample size, so do these percentages. As a result, these percentages are not exact and should not be used as such. Additionally, the fact that the standard deviation varies with sample size has significant implications for data interpretation. For example, if we want to compare 2 groups and collect 100 samples from each group, they might appear very different. These differences might become less apparent if we collect fewer samples. At least, this is the case in multiple statistical tests. So finally, when reading scientific papers, remember that the standard deviation is a prediction, not an actual measure. It varies with sample size and can become more or less inflated as a result. I hope you found this information useful and thanks for watching.